1A, name the 5 layers in the Internet Protocol stack. Almost everybody get this one correctly. The top layer is application, followed by transport, followed by network, and data link, and finally it's physical. Give two reasons why the Internet primarily uses packet switching instead of circuit switching. There are many reasons. Two of them are, well, packet switching supports statistical multiplexing, which allow more users and have a higher utility. And second is that unlike circuit switching, which require a connection setup, packet switching doesn't require any connection setup, so it's faster. So this. Part C, consider a small network of 4 hosts and 3 links, as depicted in the figure below. A 1 megabit message is to be sent from A to D. The bandwidth of the first 2 links is 400 kilobits per second, so the link between C and D is 1.6 megabits per second. Propagation delays of the links are negligible. Assume that circuit switching is used and the total circuit setup time is 100 milliseconds. What is the time to send the message from A to D? So we have situations that link A to B and B to C are both 400 kilobits per second, and C to D is different and is 1.6 megabits per second. Now, despite the fact that C and D has a faster bandwidth, the overall bandwidth from A to D is always bounded by the bottleneck, the slowest one, which is 400 kilobits per second. You can think about this as analogies of water flowing through water pipes with different diameters, and it's always going to be bounded by the one with the smallest diameter. And it doesn't matter whether the slower link is in the upstream or in the downstream. You can have the situations that maybe A, B, and B, C are the fast links. Maybe they are 1.6 megabits per second, and then C to D is 400 kilobits per second. You will still have the overall bandwidth is still 400 kilobits per second. A to B will back off from sending it so fast because otherwise it will have a build-up at router C, and then you will have a queue that is growing unbounded. So A and B will have to back off and to reduce the rates that match the final slowest link of 400 kilobits per second. So in this case, the total amount of time for sending the message to A to B will be the setup time, which is required for circuit switching, plus there are 4 other components in terms of the transmission speed, in terms of the transmission delay. Well, in terms of the delay, there are 4 components: the propagation delay, transmission delay, the no processing delay, as well as the queuing delay. In this case, there's no queuing delay because it's circuit switching. The problem isn't mentioned about the nodal processing delay, so we assume that it's negligible, and so is the propagation delay. So the only one that matters here is the transmission delay. Okay, so we plug in the numbers here. First one is 100 milliseconds. The second one, the transmission delay, the formula of that is the size of the message divided by the bandwidth. Size of the message is 1 megabit per second. 1 megabits, and then the overall bandwidth is the 400 kilobits per second. So, and you add them up, it is equal to 2.6 seconds. Okay. Last part, repeat part C by assuming that a packet switching is used with packet size 10,000 bits plus header size of 160 bits. The routers at B and C are stored forward as well as negligible queuing delay. So now the situation is that the entire file of 1 megabits is being broken up into little packets. Each of the packet carry a header information because it must store the address information, so there's a little bit of overhead. The payload here for the data is 10,000 bits, and the header size is 160. Okay, So first off, we can immediately know the number of packets that need to carry through all the message bits, which is simply the total file size, which is 1 megabit per second, divided by the payload size for each packet, which is 10,000. You have 100 packets. Okay, so now let's derive the equations that's needed to calculate the overall delay. So let's draw a timing diagram. So this is time axis. At time 0, assuming that the first packet is sent, and first packet takes time t seconds to arrive from A to D. Okay, we'll figure out what t is, but let's define t as time for one packet traveling from A to D. Okay. Now, A doesn't wait until this packet finishes arriving at D before sending the second one. It will send the second one after it sends out the first one. So after it completes sending the first one, which is just a transmission delay for the one packet, it will start sending the second one. Okay, so if this is the first packet, it will be the second one, and again the second one will take t seconds to arrive at D. Okay, so the delta here is defined to be transmission delay for one packet. Okay, and the third packet again, A waits delta seconds to finish the second one, and then it can send the third one, and so forth. So it will keep doing that until the 99th packets. Okay, this is the 99th packets, and and then after it finished 99th, it will work on the 100th one, and the 100th arrive at destination D, and that completes the transmission. Okay, so this part again is t. So the total time is, we can count from time 0, which is the first packet is sent, all the way to this, which is the end part. So if you look at that, the total time is equal to 99 delta, because there's one delta associated with all the packets except the very first one, plus you have to also consider this part of the time, which is the transmission time for the last packets to leave A and arrive at D. So that will be t. Okay, so now we have that. We can calculate, we plug in the numbers. Transmission delay for one packet, the length of one packet is 10,160 bits. Okay, and the transmission bandwidth is 400 kilobit per second. Okay, that's delta. T, well, T has three components, which is the transmission delay from A to B, plus the transmission delay from B to C, plus transmission delay from C to D. Now, since the question assumed that occurring delay is negligible, then propagation delay is negligible, so we don't have to include those components. But plugging in the numbers for these three terms, we have again, so the packet size 10,160. The transmission bandwidth between A and B is 400 kilobit per second. B and C is again 400 kilobits per second, and finally between C and D is 1.6 megabits per second. So if you do the math, the answer should be 2.572 seconds. Okay.